The Tonga Volcanic Eruption was so powerful, it sent shockwave ripples out into space. This is by The Conversation, Gareth Gorian. The ongoing volcanic eruption in Tonga, it began December 2021 with a smaller eruption, but it wasn't until 5:15 p.m. local time, January 15, that's a week ago, that the powerful explosion, the eruption occurred in this underwater submarine volcano. Nobody expected it to be that powerful. From what we have read in just today's previous articles, it's a 5 out of 5 eruption. It's still ongoing. And the ash cloud now has gone across the Indian Ocean from traveling westward from Australia. It has covered Australia, northern Australia, through the Indian Ocean. It's gone over Madagascar, and it's now reached East Africa. Now, in another 7 days, what is it going to do? Go around the world? Or reaching, definitely going over the Atlantic into South America? Now, this ongoing eruption, they said it happens every 1,000 years, such a powerful eruption. Now, it's still ongoing. It generated an enormous cloud of ash, earthquakes, and tsunamis that reached as far as the distant coastlines of Peru on the other side of the Pacific. The sound of the sonic boom was so loud, it was heard up to Alaska, even Switzerland. Now, scientists are even looking for the effects of the eruption in space. Now, the eruption column reached the Earth's stratosphere. We know that today from Volcano Discovery, they said that the ash cloud is 39 kilometers height. That's into the ionosphere. Now, the eruption column reached the Earth's stratosphere, the second layer of the atmosphere up from the ground. The sound of the explosion was heard thousands of kilometers away in Yukon Territory in Canada. And although below the threshold for human hearing, the pressure of the sound waves were even detected by barometers in the UK. Finally, support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box. This is the image of NOAA's map showing us the sulfur dioxide ash plume. It's gone over Australia, over Indonesia, and we see it going across the Indian Ocean, over Madagascar, that island to the east of Africa, and into Eastern Africa. And this, of course, is natural because we have the air currents, which are acting that way, and they're going to most probably carry it. We're going to go in, we'll see the null school to see how the currents will act and how this will travel across the world, across the hemisphere, the southern hemisphere. Now, we said that the sound pressure waves were even detected by barometers in the UK. It seems that the eruption also appears to have generated a series of so-called atmospheric gravity waves, which were detected by a NASA satellite radiating outwards from the volcano in concentric circles. And this is what you can see here. That's part of it right there. Now, scientists, including me, he says, are now looking to see what impacts these waves may be having in space. The purpose of our research is to better understand the top levels of the atmosphere, so well above where the International Space Station orbits, and in particular to what extent changes in it are driven by events on Earth as opposed to the space environment. It could also help us better understand how technology such as GPS is affected by volcanic eruptions. Because the atmosphere is mostly transparent to human eyes, we rarely think of it as a complex dynamic structure with many distinct layers. The upper tendrils of our atmosphere extend well above the Kármán line, the point 100 kilometers, 62 miles above sea level, where space officially starts. These atmospheric layers are full of waves traveling in all directions, not unlike waves on the surface of the sea. Such atmospheric gravity waves can be generated by a number of phenomena, including geomagnetic storms caused by outbursts on the sun, earthquakes, volcanoes, thunderstorms, and even sunrise. You have probably seen some of the effects of these yourself, as these same waves can create undulating clouds. Now, what's happening with the ionosphere? Such waves do not just travel horizontally, they also propagate upwards to some of the very highest parts of our planet's atmosphere, that is, into the ionosphere. This is a region of the Earth's atmosphere that extends from about 65 kilometers to over 1,000 kilometers. The ISS orbits at about 400 kilometers. So at these altitudes, atmospheric gases are partially ionized, forming a so-called plasma, meaning its molecules are split into charged particles, positive atoms called ions and negative electrons. Ionization in the atmosphere occurs due to exposure of ultraviolet radiation from the sun, high energy particles from space, and even meteors burning up. But given that oppositely charged particles exert an attractive force on each other, like a magnet sticking to a fridge door, ions and electrons also tend to recombine, once again producing neutral molecules. So there's a complex and continuous fluctuation in the ionosphere between plasma production and loss of plasma due to recombination. While these processes are mostly undetectable in visible light, they can affect longer wavelength radio light. The plasma in the ionosphere can reflect radio waves at certain frequencies, scatter them at others, or even block them entirely. These properties make the ionosphere useful for several modern technologies, including high-frequency radio communications and over-the-horizon radar. But just like at ground level, the ionosphere is subject to weather. This is caused by either the space environment, space weather that is, or by events on Earth. Space disturbances. When atmospheric gravity waves, such as this one from the Tonga eruption, generated by the volcanic eruption or any source, reach the ionosphere, they can trigger what's called traveling ionospheric disturbances. These are compression waves that can enhance the fluctuations in plasma density substantially in a short space of time and can travel for thousands of miles around the globe. These effects can disrupt modern technology, such as by interfering with the accuracy of satellite global positioning systems, GPS. Volcanic eruptions in the past have been associated with measurable changes in the ionosphere as detected by GPS receivers on the ground, for example, in 2015 and 2013. To study these disturbances in more detail than their effects on GPS, I used data from the facility called Low Frequency Array, LOFAR, one of the world's largest radio telescopes. LOFAR consists of dozens of radio antennas spread across Europe. It's designed to observe distant natural radio sources in the early universe, such as radio galaxies. The appearance of radio source in space, when viewed through ionosphere, is similar to how the view of objects through a glass of water can become distorted when we stir it or shake it up. With careful analysis, one can use these distortions to understand what is happening in the ionosphere itself. Traveling ionospheric disturbances can enhance these distortions, particularly at the radio wavelengths we use with LOFAR. The video created by Richard Fallow shows some LOFAR data from December 2013 and bright lights, natural radio sources such as distant galaxies, and showing the rapid change position fading in and out. The ionosphere, when it's disturbed, makes it shake as if we're shaking a glass of water. Now, over the coming weeks, we'll be looking quite carefully at our LOFAR data to investigate whether there are distinctive patterns visible that could be attributed to the Tongan eruption. And ultimately, the research could help us better understand how volcanoes on Earth influence space and technology. As the ionosphere is the atmospheric interference between Earth and space, it may even shed light on the precise degree to which disturbances are driven by terrestrial versus space weather events. This is by Gareth Dorian, postdoctoral research fellow in Space Science, University of Birmingham, on the conversation, Creative Commons, with some details from me given by various articles since this was written on January 20th and 2 days ago. This is on Science Alert. Please leave your comments. Thank you for your support.